And so we're going to look at periodic trends. In the periodic table. And the ones we're going to specifically look at are atomic size. That's the size of the atoms. We're going to look at ionization energy. Those are the two most important, because once you wrap your heads around those, then the next two, electron affinity and ion size, are much more easy to understand. So we're going to look at across some rows of the periodic table, and we're going to look down some columns, down some groups of the periodic table, and we're going to look at atomic size, ionization energy, electron affinity, and ion size. Okay? Okay. So first, I'm going to take you to some images from the textbook. This is one of the figures that's in the textbook, and you can see that there are, as you go across a row, like from lithium to neon, the size of the atoms gets smaller. If we look at sodium over to argon, the size of the atoms gets smaller. Okay, there's some specific reasons for that, but before we get into those specific reasons, I want to show you how that is consistent with what we did with photoelectron spectroscopy. Photoelectron spectroscopy table that we had before, or the graph. And what I want you to imagine for a second is that down here, along the bottom of the periodic table, excuse me, is the center of the atom. So we're going to imagine that this H here for hydrogen is the center of the atom. And so the distance from the hydrogen out to its outermost electron is represented by this distance on this graph. Okay?
Yeah, okay.
So if we do that, take a look at helium right beside it. If I look from hydrogen to helium and I look up and see where its outermost electrons are, it's really like a radius. It's halfway across the atom. Which one of these two sets of electrons out here is closer to the center of the atom?
The electrons from helium are closer to the symbol on the bottom of the graph.
Exactly. So if we think of this as being the distance from the center of the atom out to the outside of the atom, this would show us as being hydrogen being larger than helium. Okay. Now, when I showed you that graph, the table from the textbook a second ago, we didn't pay attention to hydrogen and helium. But take a look. Here's hydrogen, and the units they're using here are picometers, right? 10 to the minus 9 meters, the atomic radii. But look, it's 37 is what it shows up here for hydrogen. And we just said that helium should be bigger or smaller?
Helium should be smaller.
So we look over at here at helium, and we see it at 32. Pretty sweet. So this transition from hydrogen to helium, the helium atom is smaller than the hydrogen atom. So far, so good?
So far, so good.
Okay, so back here on the photoelectron spectroscopy data table, if we take this as being the hydrogen nucleus, it's slightly bigger, sorry, the hydrogen nucleus and the helium nucleus, and we look at the distance to the electrons on the outside, we see that hydrogen is a little bigger than helium. Okay?
Yep.
Now, if we jump to the next element, lithium, if we look up here at the very top, lithium has its outer electron even further away. So lithium should be bigger than helium and bigger than hydrogen. So far, so good?
Yeah, that makes sense.
Okay. And take a look. Here's lithium, slightly bigger than hydrogen. And also bigger than helium. So using this graph from the photoelectron spectroscopy, we can get some ideas about some different patterns. Okay, let's look at the next one. I've got beryllium. Should beryllium be bigger or smaller than a lithium?
It looks like the bar, the electrons, is lower down. So
Yeah.
beryllium should be smaller than lithium.
And beryllium, 113 picometers as opposed to 152 picometers. It's smaller. And so as we look at some of the trends in the periodic table as shown in this graph from the text, and we look at the photoelectron spectroscopy data, we should be able to pick out some of those things. And so if we take a look from lithium all the way over to neon, what happens to the size of those atoms as we go across that row of the periodic table?
From lithium to neon, looks like the electrons are getting closer. So the atom size should be getting smaller then.
Lithium all the way over to neon, they get smaller, just as the photoelectron spectroscopy data shows. And take a look below that now, sodium over to argon, 186, 160, 143, 117, blah, 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 all the way down to 97, they're getting smaller. We look at sodium all the way over to argon, same thing. So what I think we can say, pretty safely say, is that as we go across a row of the periodic table, as the atoms are going to get smaller and smaller. Let's look at what happens as we go down a column of the periodic table. Let's start with, as we go down the first column of the periodic table, the atom size gets, as we go down the second column of the periodic table, the atom size gets bigger. And now you can probably begin to say why that's the case if we look back at the photoelectron spectroscopy and I say, what happens as I go from hydrogen to lithium to neon, to sodium and to potassium? 3.55, 0.5, 0.42, they get bigger as we go down that column. And why do they get bigger? Because we're at the outside electrons are in an orbital further and further away from the nucleus, just like we had with our energy level diagrams.
I've never really learned the periodic trends through this PES graph, so I think this is another great use for this graph and another great way to learn some of these periodic trends. So and this is just one of them. We'll see more.
Hopefully. So if we look at atomic size, we see that as you go across a row of the periodic table, they get smaller. And as you go down a group of the periodic table, they get bigger. Okay, so that's one of the patterns. I said we were going to do atomic size. Now we're going to do ionization energy. Okay?
Yep.
Now, the trick with ionization energy is to figure out what is ionization energy. So ionization energy is the amount of energy required to remove an electron. From an atom. Okay? And for what it's worth, we've been doing this since day 2 or 3 of the course, because when we do the photoelectron spectroscopy experiment, we're trying to find out how much energy does it take to remove an electron from all of these orbitals. That sounds like, hold on, it's the amount of energy required to move an electron from an atom. That's what that was. We were ionizing each one of those atoms. But in the photoelectron spectroscopy experiment, we are moving all sorts of different atoms, or sorry, all sorts of different electrons. But in the ionization, we're going to worry about just the outermost electrons in thinking about it. And it's all there sitting waiting for you, just like it was, like it was last time we did this. Take a look. If I look at hydrogen and I want to remove an electron from hydrogen, apparently this outermost electron, or this one electron, takes 1.3 megajoules per mole to remove it. To remove the electron from lithium, it's 0.52 megajoules per mole. Is that more energy or less?
Less.
0.52 is less than 0.13, so it has less, takes less energy. Take a look over at sodium. Sodium's at 0.5. So 1.3, 0.52, 0.50, and just tucked up here in the corner for potassium is 0.42 megajoules per mole. So the removing one electron from the outermost orbital of each one of these elements in group number 1, the value gets smaller going down. Here we had hydrogen at 1.3 megajoules per mole. Here we have hydrogen at halfway between 1,000 and 1,500. Oh, but look, this one is in kilojoules per mole. So it's about 1,300 kilojoules, exactly 1.3 megajoules, the exact same value. And so if we look at hydrogen, then we look at lithium, then we look at sodium, we see the value of the ionization energy is going down. So as we go down the periodic table, as we go down from hydrogen to lithium to sodium to potassium, the ionization energy decreases. It's easier to turn a potassium into an ion than it is to turn a sodium into an ion, or than to turn lithium. So these elements down at the bottom left-hand side of the periodic table are easier to ionize than the ones elsewhere. Kevin, do you want to make a comment about that at this point?
Yeah. So when we go down a column, we decrease the ionization energy. And what about if we go through a row of the periodic table?
So going across the row. So going from lithium to neon. It looks to me like going from lithium to beryllium. Boron seems a little bit out of alignment there. Carbon, nitrogen, oxygen. But generally speaking, going across across a row of the periodic table, the ionization energy increases according to this graph. So this is looking at lithium over to neon. Okay, so removing an electron from lithium and then removing the electron from beryllium, one of those is easier than the other, isn't it? Lithium is easier than beryllium. And then, oh, remember we saw that with boron was a little bit out of alignment, and then carbon, nitrogen, oxygen, fluorine, and neon. Gets successively harder to do it, just like it showed in the table in the text. Gets harder going from lithium to neon. You want to look at the next row?
Sure thing. Let's go.
You don't need to look at my table. You've got your own, but here we go. Look at my table if you want to look at mine. Take a look what happens. Going from sodium down here at the bottom to argon, going from sodium to argon, they generally get harder to remove, just like it shows in the graph from the text.
Yep.
Going from sodium up to argon, harder. It also, by the way, we can now start to see, using the photoelectron spectroscopy data, about some of these exceptions. Take a look at boron. Why is boron easier to ionize than beryllium? So, as I was saying, boron was an exception. It's a little easier. Well, when we remove this electron from boron, we end up with an empty orbital. And we know that completely empty and completely full orbitals are a little bit more stable, a little bit more favorable. And so removing this single electron from boron is a little easier than removing one from its neighboring beryllium. Likewise, with oxygen, when we remove one electron from the 2p for oxygen, we end up with 3 half-filled orbitals. And we know that half-filled orbitals are a little bit more stable. And so it's a little easier to remove this single electron from the oxygen than it is to remove it from the nitrogen. So that helps to explain why we see some of those exceptions. So it being a smooth line that we're going across.
Yeah, okay.
Sorry?
Hmm?
Is that better that way?
Yeah, that was, we could definitely see that.
Okay, thank you. Alrighty, that's looking at atomic size and ionization energy as they change as you go across rows of the periodic table and down columns of the periodic table, and linked to the photoelectron spectroscopy data that we looked at that we developed in the first couple of days of the course.
Yep.
So what we'll do next, maybe next time, is we'll look at electron affinity and ion size.
Sure thing.
How does that sound to you?
Sounds like a good idea.
Okay, perfect. All right. Thank you, Kevin.
Thank you, Dr. Hunter.